1, 2, 3, 4, 5. We are now going to use what I call the formal definition of a derivative to determine some derivatives. Let me just give you a quick overview of why this is important. So here is the graph I used previously. I didn't tell you at the time, but this actually, the equation for this graph is, let me do it, I believe you can see it well. F of x equals x squared over 4. If you want to, you can think of this as y equals x squared over 4. So each point on this graph, you could plug in the x and the y in this equation, and it'll work. 0, 0, you plug in 0x, 0y, it works. Look at here, if x is 2, y should be 1. You plug in 2 for x, y is 1. How about when x is 4, y should be 4. You plug in 4 for x, 6 and 4 is 4. All right, so that's the equation of this graph. So what's the big deal with, what is the derivative telling us? The simplest and most important thing to remember is the derivative of a function or equation is the same thing as the slope. We said earlier, a lot of times we want to find the slope of the line. This is a curve. The slope is always changing. How can I find the slope? Well, I can choose a point and draw a tangent line and jump through hoops and do all kinds of crazy things. Although now we have a way to do a calculation such that I'm just going to tell you right now, I'm going to write down the derivative of this function. In a minute, we're going to actually work these out. But for now, the derivative would be x over 2. Why is that important? Remember what I told you about these curves? The slope is always changing. If someone says, hey, please give me the slope of this curve, my question is, well, you tell me where you want to look. You give me a point on the curve, and I'll tell you the slope. So if they want the slope right here, then I can try and figure out the slope here. But that's going to be very different if they want the slope over here. Well, what the derivative does, the derivative calculates the slope. Just for fun, let's just say someone says, find the slope, and I say where, and they say, okay, well, find the slope when x is 0. So we go to our curve when x is 0. What would the tangent line be? It'd actually be a horizontal line. I go to my formula. I plug in 0. 0 over 2 is 0. What I'm saying is, for this curve, when x is 0, the derivative or the slope at that point is 0. And I look here, yeah, the slope is 0. I look at my tangent line, which is the same as the slope of my point. It's horizontal. We know that the slope of a horizontal line is 0. How about someone says, well, hey, what's the slope of this curve when x is 2? Well, x is 2 is right here. Maybe I'll use my pen to be a little more precise. So the slope of here is like the tangent line. So let's just draw the tangent line just to see what it should look like. But I don't even need to do this graph because now that I have my first derivative, I plug in 2 in for x. 2 over 2 is 1. Now this may not be totally precise, but it's pretty close to where, if you look at this tangent line, and we were trying to find the slope, if I go from here to here, rise of 1, a run of 1, looks like the slope there is 1. Well, I didn't have to do the graph and stuff because I was able to calculate the first derivative. I just plugged in x is 2 and I got it. I mean, we could do one more. Let's say up here when x is 6. Someone says, well, what's the derivative of this curve or this line when x is 6? And I say, well, I can give it to you pretty easily because I now have already calculated. I have a formula. I have an equation for the derivative of this graph. I plug in 6 for x. 6 over 2 is 3. Now, when you draw tangent lines, it's not always the most precise thing. So if this isn't perfectly right, don't hold me to it, but maybe it'll sort of be close. So maybe here's the tangent line. The slope of the tangent line should be the same as the slope of this point. So if I go try to figure out, maybe if I go from here, 1, 2, 3, 1, rise of 3, run of 1 is 3. Yeah, looks about right. So the beauty, the power, the use of the derivative is you're given, I was given a function or an equation. But what I really want to know is I want to know the slope of this equation. Well, the slope is going to be constantly changing. But what I can do is I can calculate the derivative. And once I have the derivative, you can tell me wherever you want. You give me the value of x, I'll give you the slope at that point. So if you say, well, how about check out when x is 0? Boom. First derivative when x is 0 is 0. Does that look right? Yep. How about give me the derivative when x is 2? Okay, you plug in 2 into my derivative equation, you get 1. If I look at my graph, does that look correct? Yeah. How about when x is 6? So the power of a derivative is the derivative gives us the ability to easily calculate the slope any place on the curve. It's just a formula, you plug it in. So now what we're going to do now is we're going to take some functions and we're going to use the formal definition of a derivative and calculate the derivatives. Now let me just be honest and tell you this. What we're going to do in the next few minutes, this may be the last time you'll do it because this is going to sort of be what I call the painful way to figure out the derivative. After this lecture, we're going to give you a bunch of shortcuts where, to be honest, some of the problems we're going to do now may take 3, 4, 5 minutes. And when you use a shortcut, it may take 30 seconds. And you'll never probably use the long way again. But like a lot of math, sometimes they want you to do things the hard way and then maybe appreciate the easy way. So the whole key is, if we're given a function, f of x, this is how we're going to calculate the derivative. Just sort of ugly. We use this difference quotient. But it's the limit as h approaches 0 of all of this. So how does it work? Pretty straightforward. We have function x squared we want to calculate the derivative, and then once you calculate the derivative, just for fun, we'll maybe ask to actually find the slope or the derivative at these values of x. We'll just do a couple. So here's what you do. You have to take this function and you have to apply this formula. So it's the limit as h approaches 0, f of x plus h. Well, here's my f of x. So f of x plus h is, right, you put x plus h in every time you have an x. So it's going to be x plus h squared, right? Since it's x squared, f of x plus h would be x plus h squared, minus f of x. Here's f of x, so minus f of x all over h. The h doesn't change. So what I'm going to do now is I'm going to simplify all of this, and then we're going to apply what we learned about how to calculate limits and then take the limit. So let's first see how this thing maybe simplifies, and then we'll take the limit. So what I'm going to do is x plus h squared, I have to FOIL it, right? Because it's x plus h times x plus h. So it ends up being x squared plus 2xh plus h squared. So that's multiplying out the parentheses. I've still got the minus x squared, and it's all over h. So now, if I combine like terms, I have x squared minus x squared. It's nice. Those cancel out. Then I have 2xh plus h squared over h. Now you notice I have two terms in the top, and they both have an h in it, and I have an h in the bottom. So I can actually cancel an h out of all three of these. So this is going to simplify further. I'm left with 2x plus h. Now if you remember how to take the limits, right? First attempt at taking a limit, you just put the number in for the variable. And if you get something that's okay, then you're done. So if I put in 0 for h, end up with 2x, which is perfectly fine. So that's my derivative. So my original function was x squared. The derivative is 2x. And I came up with this by applying this formula here. Now just for fun, once you find the derivative, then they say, well, just for fun, so how about what's the derivative going to be when x is 2? So derivative, you plug in 2 for x, 2 times 2, it's 4. How about when x is minus 1? What's the derivative? Plug in minus 1 for x, negative 2. So once again, you're given a function. Say we want to be able to find the slope at all kinds of different points of this function. The way we do it is we first find the derivative, and once you have an equation or formula for the derivative of that function, then you just plug in the values of x, and it's just a simple calculation. All right. How about I will do one more, because these can get very messy. This one I'll do, instead of function notation, Sometimes they will just give you something like this. Now, since it's y and x, if they want the derivative, a lot of times you'll see it, write it with this dy dx notation, right? This means derivative. A lot of times we say the derivative of y with respect to x. So once again, I'm going to use this formula up here for my derivative. So in a sense, this is sort of like my function, right? So dy dx, f of x plus h means I take this function, I replace x with x plus h, right? So this right here is f of x plus h, right? I put in x plus h for h. Then minus f of x, well, f of x is this, f of x and y are the same. But I put this whole thing in parentheses and I subtracted the whole thing. All of this over h, and I forgot to write in the limit of that as h approaches 0. So once again, let's simplify what's inside the limit, and we'll take the limit. So if I multiply out the parentheses, 2x plus 2h minus 4. Now this minus gets applied to both terms inside. Minus 2x plus 4 all over h. Now see if I can combine like terms. 2x minus 2x, those cancel. I've got negative 4 and 4, those cancel. I'm left with 2h over h. Actually, the h's cancel. So I end up with the limit as h approaches 0 of 2. Of course, there's no h's even in here, so it's just going to be 2. So what's interesting is the derivative is just a number 2. Derivative is a constant. Does that make sense? Well, it does, because look at my original equation. What is this? This is the equation of a straight line. The derivative is the same thing as the slope. What do we know about the slope of a straight line? It's constant. It doesn't change. That's what this is saying. It's always 2. Doesn't matter where you're looking on the line, it's always 2. So, oh, that makes sense. Let's do one more. Maybe I'll do, how about, I'm just going to make this up. Y equals x squared minus x. So just in case it's not clear, since we're doing function notation, I can also think of it as f of x equals x squared minus h. So once again, I got to apply this definition of a derivative to this function. So I'll still call it dy dx. So the limit as h approaches 0. So here's f of x. I've got to replace x with x plus h. So it's going to be x plus h squared minus x plus h, right? So this is f of x plus h minus f of x x squared minus x all over h. So you can see why. I mean, I'm telling you now, in the next class, when we learn how to take this derivative with sort of like the shortcut, the easy way, this problem takes 20 seconds at the most. And it's probably going to take me 5 or 10 minutes to do it the long way. So there's hope in sight, even though this is painful for now. It won't last forever. Got to multiply out these parentheses, FOIL that, x squared plus 2xh plus h squared minus, the minus gets applied to both terms inside. This minus gets applied to both terms inside. Minus the negative x is plus x. All of that over h. So let's try and combine like terms. See what I've got. I've got an x squared minus x squared. I've got negative x plus x. So normally if you do these problems correctly at this point, a lot of things always cancel out. I think that's it. So let me see what we have left now. I've got 2xh plus h squared minus h all over h. Of course, look at all three terms in the top have an h and there's an h in the bottom, so I can cancel an h out of all of these. And I'll have 2x write this more clear. So when you cancel the h here, you're left with 2x. When you cancel the h squared over h is just h. Negative h over h. So it's not 0 here. It's actually 1. Now if you take the limit, right, first attempt at a limit is just plug in the number in for the variable. If I plug in 0 for h, I'm left with 2x minus 1. So therefore, the derivative of x squared minus x is 2x minus 1. Now just for fun, once you calculate derivative, remember with f of x, if I want to know the derivative when x is 2, I did this. What do you do here? Sometimes you may see it written like this. Say they want to find the derivative when x is 1. They sort of draw this line here. And that means stick in 1 for x and find the derivative. Or what if they said, find the derivative when x is negative 2. So you put in negative 2 for x. And there you go. All right, so these are a few examples of the long and painful way to calculate derivatives. In the next lesson, we'll start learning some of the shortcuts, and you'll find it's actually pretty easy to take derivatives.